Hello, students. This is Mr. Allen, and today we're going to finish chapter 8. We're also going to start chapter 10. You'll see why we need to do 10 today. I would encourage you to watch the first part of this video, which is section 8.4, and then save the second part for later. But you can watch both parts together if you'd like. So here we go. Our objectives for section 8.4, which is on angle of elevation, is just to use angles of elevation and depression. In section 8 or 10.6, we're going to look at circles and arcs, and we want to be able to find the measures of central angles and arcs, and we want to be able to find circumferences and arc lengths. All right, so let's start with angle of elevation and depression. So let's just kind of cut to the chase here. I've got all the text already written here on this slide. This is right out of your book. But you can see that there's this guy up here flying in a hang glider. And if we draw a horizontal line that's parallel to the ground, and then if we make this line that goes down to the person on the ground, this angle right here is called the angle of depression. It's the angle that goes down. The angle of elevation, then you'd be the girl on the ground. Again, you look at this horizontal line. This angle that goes up from the ground, or her eye level parallel to the ground, up to this line that goes up to the hang glider, that's called the angle of elevation. So here's a very simple example. It says, what is a description for the angles related to the situation shown here? So we can see we've got a bird, we've got a mountain, we've got a guy in a balloon. So the first question is about angle 1. So what is angle 1? Well, again, if we look at the horizontal line, this angle goes down. So this is an angle of depression. Angle of depression. And then for part B, we're supposed to look at angle 4. Well, here's angle 4. So here we're looking, this is ground level, and then we're looking up to the balloon. That's going to be an angle of elevation. So that's the first thing that you need to be able to do, is just recognize what's an angle of elevation versus an angle of depression. And there's a couple other angles we could talk about in this problem as well. You know, I could ask you what kind of angle is angle 2? Is angle 2 an angle of elevation or depression? I'll let you figure that one out. Okay, let's look at an applied problem. Now, for this problem here, you are going to definitely want to have a calculator. I've got a couple here. I've got a scientific calculator, which is what you might have, and I've also got a graphing calculator. And on both of these calculators, whatever one you're going to use, and I'm just going to assume you're using one like this, you want to make sure you're in degrees. And the way to check that is when I turn this on, this is a TI 30X. Down in small black letters, it says DEG. That's degrees. If yours is not in degrees, yours might, for example, say RAD, or it may say something else. You need to go to, there's a button on here at the top. Let me get my camera here. There's a button on here at the top right here that says DRG, and you want to make sure that you're in degrees. Okay, we're going to do degrees. So it says, suppose that you stand 53 feet from a wind turbine. Your angle of elevation, so they're telling us it's an angle of elevation, is 56.5 degrees. Your eyes are about 5.5 feet above the ground. Approximately how tall is a turbine from the ground to its hub? So what we're basically trying to do here is we just want to figure out what this distance here is of x. Okay, we just want to figure out what x is. Okay, so we know that this triangle, there's 53 feet here. We know this angle of elevation, and we're just trying to figure out what that x is going to be, that distance there. So this looks like we are going to have to use, this is the opposite leg. This is the adjacent leg. So if we have opposite over adjacent, I think that's tangent. So we're going to need tangent of theta. In other words, and here's the key, the tangent of 56.5 degrees is going to be equal to x over 53. This is the equation that we need to solve for this particular problem to figure out that distance x. So to find x, well, we could just figure out what tangent of 56.5 is, and I'm just going to use my calculator, and all you're going to do is do 56.5, and then I'm going to hit oops, I guess that's incorrect. That's my other calculator. Let's try that again. You have to actually press tangent button first, and then 56.5, and that gives you the following answer, 1.5108 3, etc. That's equal to x over 53. And then, of course, we just cross multiply here. So multiply that answer by 53, and you will get an answer of x is approximately 80.07 feet. That's that distance x. Now, if this distance here happened to be this 5.5 and you wanted to know this entire distance, then you would take that last answer and you would just add 5.5 to it. So that total distance there, if you needed to know that, would be 85.57 feet. Okay? So make sure your calculator is in degrees and that you know how to do that. If you need help, let me know. I'll be glad to show you how to do that. All right, so let's do one more problem in this section, and then we'll move on to section 10.6. So this is a gridded response problem, and it says to approach runway 17 of the Ponca City Municipal Airport in Oklahoma. The pilot begins his 3-degree descent. That's his angle of descent. That sounds like an angle of depression. Get the red ink on here. So here's our angle of depression. And he's starting at 2714 feet above sea level. And the airport is 1,007 feet above sea. Okay, so now this is interesting. So we know that sea level, so let's pretend this is sea level. We know that this is 2714. We know that this distance, the airport, is 1,007 feet above sea level. And they want us to figure out to the nearest mile what this total distance is. We want to figure out basically what this is here, this length here, x. Okay? Now, here's the thing. This one's a little tricky because they've told us that the total from sea level, the plane is 2714 feet, and the airport is above the sea level by 1,007. So it turns out that this distance right here is going to be the 2714 minus 1,007, which is 1707. So this is 1707 feet. So that's, and by the way, this is in feet. I should note this is in feet, okay? That's a 0. All right, so we've got the following triangle. This is 1707. We want to know what this is, and we know that this little angle of depression is 3 degrees. All right, so in this case, we've got the opposite leg and the hypotenuse. So that's opposite over hypotenuse. That's sine. Oh, I'm sorry. Yes, no, that's right. It is. That's sine. Good. We want to make sure we're got the right ratio there. So that's sine. In other words, to do this problem, we're going to have to say the following. We're going to say that the sine of 3 degrees is equal to 1707 over x. That can be, if we cross multiply and then divide, if we multiply both sides by x, we would get x times sine of 3 equals 7. In fact, let me just write that. X times the sine of 3 equals 1707. In other words, that can be then divide the sine over the other side. So x is equal to 1707 divided by the sine of 3. And now we can just go ahead and do that with our calculators. I'll go ahead and do that now. So we're going to do 1707 divided by the sine of 3. And that gives us an answer of x being 32,616.199 feet approximately. But here's the tricky question. It says to the nearest tenth of a mile. So to do that, you have to know how many feet are in a mile. And it turns out that it is 5,280 feet is equal to 1 mile. So we need to divide our answer. So we're going to take our last answer there, and we're going to divide it by 5,280. And you will get a final answer of 6.2 miles. That's your final answer. It is not that 32,600. That was in feet. The question wants it in miles. Okay, guys, so that wraps up section 8.4. Now I'm going to start section 10.6. So if you want to pause the video and come back to this later, you can. So we're going to move on to chapter 10. All right, so again, this is section 10.6. Okay, this is on circles and circumference and radiuses and diameter. And I know you probably know most of these things, but let's just go ahead and run through them again. So this shape right here is called a circle. And a circle is just all the points that are equidistant from a point called the center. So here P is the center. We know that this segment here, AB, this is called a diameter. It goes all the way across the circle and hits the center. We also have this thing here called the radius. The radius starts from the center and goes to the circumference. There's also, when we get down here, congruent circles. Congruent circles just mean circles that have the exact same radius. They're the exact same size, and of course they have to have the same shape. And then there's this thing called a central angle. Let me erase what I've written in here for a second. A central angle just means this, like right here. This is a central angle. In other words, it's in the center. It's like the center. It's formed with the center of the circle. So angle APC is a central angle. So it's under, those are things you've probably already learned back in middle school. By the way, this is the notation for circle. We would call this circle P. That's the notation. The other thing we got to keep in mind is we have these things called arcs. So for example, this red arc, that is a minor arc. And the reason it's a minor arc is because it's less than 180 degrees. And you might say, well, how do you know that that's the measure of that? Well, we'll get to that in a minute. But it's also what we call less than a semicircle. And by the way, a semicircle is half of a circle. And a major arc is more than a semicircle, or more than 180 degrees. And again, we'll talk more about how I know those things in a minute. So we got major arcs, minor arcs, etc. So let's look at an example. And I'm not going to give all the answers. I'm going to give most of them. Okay, this section is actually pretty simple. So here's circle O. They want us to give the minor arcs. I'm not going to give all the minor arcs, but I'm just going to give you a few. So this right here, this AD, you just write AD, and then you put like an arc over it. That is a minor arc because it is less than a semicircle. Remember, a semicircle, in fact, let's just go ahead and do a semicircle right now. What are the semicircles for circle O? One of the semicircles would be this right here, and we would call this DAC. That is a semicircle because it is half of a circle. Now, the reason I put the A is I wanted to differentiate that from the arc DEC. Arc DEC is this semicircle over here on this side. Okay, so those are different semicircles. And by the way, there are others. I'm not going to give you all of them right now. Let's do another minor arc, though. Let's do a minor arc in green here. So another minor arc might be, DE. DE is a minor arc. So again, you just write DE, and then you put an arc. For minor arcs, you only give 2 letters. For major, and I'm going to get to major arcs. In fact, let's do that now. Major arcs and semicircles, you're going to give 3 letters. So let's do another major arc. And a major arc, remember, has to be more than a semicircle. So a major arc might be, let's just give you one here. Let's go from here all the way around to there. That would be arc DEA. By the way, you could also call it arc DCA. That would be another equivalent name. Let me give you one more major arc. I don't know. I'm just going to make it this one up. Let's do this one right here. I'm going to give you this one. Okay, so this would be arc, we'll call it CAE. Now here's the thing. The first and last letter has to be where the arc begins and ends. And then the middle letter just has to be somewhere along the path of that. So major arcs and semi circles have 3 letters. Minor arcs only have 2 letters, and then you just put the arc symbol over it. I think that's pretty easy to understand. Okay, so I've already kind of mentioned this, but I maybe should not have. This arc right here, this arc, we measure it. One of the ways we measure it is by its central angle here. So this central angle is 50 degrees. So we would say that the measure of that arc, that minor arc, is 50. So that's why earlier when I was talking about less than 180, this is a minor arc. RT is a minor arc because its measure is less than 180. In this case, it's 50. And the way you would write that is you would say the measure of arc RT equals 50. And it's equivalent to the measure of its central angle. So this is a key idea. All right, this is something that you maybe didn't know. Now look at this major arc right here. You see this major arc? Its measure is 310. And the reason it's 310 is a full circle is 360, but then you have to subtract that minor arc of 50. So 360 minus 50 is 310. So that's a major arc. So major arcs measure more than 180, minor arcs measure less than 180. And if they measure exactly 180, we call that a semicircle, and that's mentioned right here. Now, hopefully you remember angle addition postulate and segment addition postulate. We also have arc addition postulate, and basically here's what it says, and I think it's pretty intuitive, but let me explain it. If the measure of this arc is, let's say, I don't know, 30, and let's say the measure of this arc, which is also a minor arc, let's say that that is, I don't know, let's just say 120, then what is the measure of arc ABC? Well, it's simply 30 plus 120, which is 150. Does that make sense? So you got 30 plus 120, 150. So that's arc addition postulate. So let's look at some examples of that one. What is the measure of arc BC? Well, the central angle is 32, so the measure of arc BC, I'm going to write the measure of arc BC is equal to, well, it's the same thing as the central angle, so it's the measure is 32. What's the measure of BD? Okay, so BD, let's do this one in, let's say, red. That's this whole thing here. So I have to do the measure of BD is going to be 32 plus 58. So that's going to be, let's see here, I think that's 90 degrees. Oh, that's interesting. That means that this angle right here has to be a right angle. Now notice that in the diagram, in fact, let me erase what I have there in the diagram. Notice that in the diagram, they give you a central angle and then they give you the arc length of 58 degrees. So they're trying to reinforce the fact that those are equivalent. Okay, what about arc ABC? Well, I hope that one's an easy one. That's a semicircle, so it has to be 180 because it's a semicircle. And then finally it says, what is the measure of arc AB? What is the measure of arc AB? Well, the measure of arc AB, that has to be 180 minus that 32 degrees that we mentioned earlier, that 32 degrees. So that's got to be 148 degrees. That's the measure of that particular arc. Okay, we're doing good. We're almost done. Okay, we got 2 more things and we'll be done. Circumference of a circle, you guys already probably know this as well. Again, this is something that you were taught in pre-algebra. So circumference, most of you are probably more familiar with this. Circumference is 2 pi r, and circumference is pi times diameter. Now remember, circumference is the total distance around a circle. This is different than the arc measure. This is what we would refer to as arc length, and this is actually the measure of the entire distance around a circle. So Anyway, so for example, let's say that I said that r was 3, then the circumference would be 2 times pi times 3, or what we would call 6 pi. That would be the total circumference. All right, example 6. We've got one more example after this and we'll be done. It says determine the total distance around the track. Okay, so we've got a couple of things going on here. Remember, if you go around the track, you go all the way around here like this. Well, the first thing that I would notice is that this distance from here to here is 60. And this distance from here to here is also 60. So far we have 120 feet. Now we also need to figure out the distances from here into here. Well, those are both semicircles, so we could put those together and make one complete circle. We know that the diameter of that circle is 25 feet. So I can use my circumference formula, which is pi times diameter. So that'd be pi times 25. So that tells me that's the circumference of this circle. So that tells me that the total distance is 120 plus 25 pi, and that would be feet. This is the answer in what we call leaving it in terms of pi. Now, if you want to know what that is exactly, or not necessarily exactly, but as close as you can with a calculator, let's just go ahead and do that right now. 120 plus 25, and your calculator should have a pi button on it. Mine does. And I get this is approximately 198.54 feet. That would be the total distance around the track. This here is in terms of pi. This answer over here is the decimal approximation. All right, last big idea, arc length. So if I want to, now we're not talking about arc measure, we're talking about the length. If we wanted to talk, how far is it to walk along that path? This formula is probably the hardest of all the formulas, but here it is, okay? It can be written either way. I'm going to tend to use this top one, but the measure of the arc length is simply the measure of the arc divided by 360 times 2 pi r. Okay? And basically what this is doing is this is giving you the fraction of the total circumference. So this is circumference, and then this is what fraction of that. So that was circumference, and this is the fraction of the circumference. Let's just look at an example. So this is the last examples, and we'll be done. What is the length of the arc shown in red? So here our arc shown in red is right here. We know that first of all, let's make sure we know what the radius. We know that the radius here has to be 8 because the diameter is 16, so half of 16 is 8. We want to find this right here. Oh, what's this central angle? That's 90. That tells us that this arc length is 90, or I'm sorry, the arc measure. Let me write that. The arc measure is 90. So that is, the arc measure is 90. So we're going to now use our formula that we had on this last slide, and we're going to say that the length of arc xy is equal to, and we're going to do 90 over 360 equals, oops, not equals, I got to put times in there, times 2 times pi times r. And what was r again? 8. So we've got to put all of that in our calculator or work it out. So 90 over 360 turns out to be 1/4, and 2 times 8 is 16. 1/4 of 16 is 4. So the answer here is 4 pi, and the units here is inches. So that's our answer. And notice I'm leaving this in pi because it tells us to leave our answer in pi. So again, I just used the formula here. The arc length is equal to the arc measure divided by 360 times 2 pi r. Last question. We're going to do the formula one more time. Here we know what our radius is. It's 15, so that's easy. So r is 15. So to find the length of our major arc, this is a major arc, okay, its measure is 240, and I'm going to call it xpy, using 3 letters because it's an arc. That's going to be equal to 240 over 360 times 2 times pi times the radius, which is 15. And so you're going to I would just use your calculator. I would do 240 divided by 360. You're going to get 2/3. And so you're going to have, in fact, let me just show a little bit of work here. You're going to have 2/3, and then 2 times 15 is 30 pi. And so you're going to get 20 pi, and the units here are centimeters. So it's 20 pi centimeters. That is going to end our presentation for the day.